All right. Hey, everybody. Okay. So, to start step three here of analyzing your images, here I am on my Google Drive for my Maricopa account, just like you should be. And I've made a folder on my Google Drive called Exotic, which is the name of the software. And then I've got a bunch of folders of images from the last few years. Um, you probably should just have the one folder with your images. So, um, you know, and the images will all have names. The file names will all look like this. But if if you have your folder still has the default name from the telescope, you probably want to name it something simpler because you're going to type this out in a minute, and so you're not going to want to have to remember what the actual name of the folder is. So change it to I think for demonstration purposes today, I'll analyze these images of Hat P32. So name your folder something simple. And then once you've got that all up and ready, go to the organization is called Exoplanet Watch. So if you just Google Exoplanet Watch Exotic, that should take you to this page. And then they've got sort of three versions of the code. We are doing something where we're using our own images. We're gonna use Exotic's code to analyze our own images. So that's the advanced version. So go ahead and click on that right there. And this code is all a Python code that's going to be run on this Google space. And here it's changed my account to sort of my normal Gmail account. So I'm going to make sure that I switch over to my Maricopa account because you need to be logged in with this Google collaboratory space using the same account as you have the files on the Google Drive. So switch to your Maricopa account here, and we should be ready to go. So let me walk you through. Basically, each of these play buttons is a step. Each of these steps is going to execute some code. So here's the code. You don't need to worry about that at the moment, so we can close that. But you're just going to go through and push the play button on each of these steps and run them in order. But there are some steps here involved. So let me show you what you're going to do. So for step one, load the Exotic Programs libraries, and then you're going to mount your Google Drive. Here's what happens. So you're going to press play. It's going to say, you sure you want to run somebody else's code? You say, yeah, run it anyway. And if I remember correctly, they updated the code not too long ago, and something is a little glitchy. So the first time that you go to load these libraries, it's probably going to fail, and then we need to reload them. So let's see what's going to happen here. It's loading styles. Okay, yep. The following packages didn't work. You must restart the runtime in order to use newly installed versions. Okay, so here's what you do. Go. Should we let it run? Probably not. Ooh, it seems to think it can run. Let's let it run until it actually fails. You'll know it's failed when that play button turns into a red button. So let's see if they actually have it fixed. Okay, let's see what happens here. I'm going to shrink this window down. Oops. Nope. That's not what I want. There we go. Shrink my Chrome window down so that it's easier for you to see what's going on here. Okay. I think this isn't going to work. So let's stop this. Okay, nope. Stop. Okay. What you're going to do in order to restart the runtime is you go to this menu here that says runtime. You're going to click restart runtime. You sure you want to restart the runtime? Yes. Okay. When this menu down here gives you the green check mark, you can close this. Then that means, okay, everything should have been restarted, and now we should be able to click this button, and it should load successfully this time. Usually you have to restart the runtime just once. If it doesn't work the first time, then do it again. But it should load okay now. There are 5 libraries that it has to load, and you'll see it count 1 out of 5, 2 out of 5, etc. Okay, so it's loading number 1, number 2. Number 2 is the big exotic code, and then 3, 4, and 5 I think are pretty short. So this will take a minute. I'm going to keep on recording, and so if everything runs correctly, then when I go to post this video, I'm going to do an edit and cut out all the time of it just sitting and loading these libraries. So if everything goes correctly, then I'm probably going to stop here and jump forward in time. Okay. I actually did have to restart the runtime again when it failed the first time, or second time actually, but seems like it's working the third time here. Once all 5 of the libraries are loaded, it's gonna pop up this window and ask for your permission to access your Google Drive. So you say connect to Google Drive. You'll go click on your Google account, the Maricopa account there. You'll click on that, and you'll scroll down to the bottom here, and you'll click allow. And now the program has access to your Google Drive so that it can go grab the images off of the Google Drive. All right. All right. And then when you see the check mark next to step 1, fantastic. It says done. It's mounted your Google Drive. You can move on to the next step. All right. So now let's load the images. Click on that. Click on step 2. And it's going to ask you, okay, which folder has your images in it? So if you named it like mine, it's the exotic folder, and then within that, it's the folder that I am going to access is HATP32. That's the name of the folder. All right. It found 453 images. That's going to take a while. Okay. So now that it's got the images, name the exoplanet target. Okay, so I am gonna actually look at images of the transit of HAT P32b. Now notice, remember how exoplanets are named, right? The star is HAT P32, and then HAT P32b is the name of the planet. They want the name of the planet, so I'm going to give them this full thing here. For example, if you're analyzing WASP 22b, right, the star is WASP 22, WASP 22b is the name of the planet. So give it the full planet name and then click return. It's going to go look for information about HAT P32b in the NASA Exoplanet Archive so that it can get all this valuable information about the planet. And now it's ready to analyze our images. Here you can enter an observer code. So basically, if you enter, the AAVSO is an organization that collects information about variable stars, like, say, a star when a planet transits in front of it. And so if you enter your observer code, then the code will send your observation directly to this organization, which you could do if you really want to. And I think, at the end of the semester, we might want to do that just so that our observations can be added to everybody else's and help people understand what these planets are. But for right now, if you want to skip this step and then come back to it later, then we'll just hit enter again and skip this step. All right, so it says done. We can move on to the next step. Fantastic. Okay. For step 3, All of the telescopes we're using have a field of view of 30 arc minutes, so let's leave that as the default. The star that I'm looking at is HAT P32, so I can leave that as the same. If you were, like I said, if you were looking at WASP 22, then you would put that, or WASP 32, or WASP 104, or TOI 5555, whatever. Like, that's the name of the star. So since I am actually looking at WASP or HAT P32, I'll leave that as is. So you put in the field of view, which should just be 30 arc minutes. I think that's the default, so leave that as is. Put the name of the star in there, press play, and it's going to... I'll show you what's going to happen here. Here's where we have a little bit of work to do, because it is going to pull up your first image in the folder. So here is my image, where instead of black and white, this picture is from blue to yellow. So the stars are the yellow and the blue is the dark sky. Here, overlapping it, inconveniently enough, here is a star chart from the AAVSO. And the AAVSO, again, that stands for the American Association of Variable Star Observers. And so when you're looking at a variable star, like an exoplanet host, in order to measure the change in brightness, we want to compare the brightness of our star to some non-variable stars, right? We want to be able to tell that the brightness of our star is changing by comparing it to some stars whose brightness does not change. And so the AAVSO makes these handy star charts and then numbers these stars, and these stars are good comparison stars because they don't change brightness. So now we need to first off find out where our target star is, and your target star should definitely be in the middle of the image. But where exactly? Okay. So compare this to this and try to match some stars. Now, like these two bright stars and then this third one over here sure looks a lot like this. So I would bet your image from your telescope could be rotated in some way, and I would bet that if those two bright stars and that one are the same as those, then my image needs to be rotated counterclockwise in order for my image to line up with this. That's a reset button. I was hoping that might be a rotation button, but it's not. I don't think we can rotate the image with our menu here. So we're just going to have to mentally rotate either this image or the star chart so that they match. Okay. So if those two bright stars are those two, then it sure looks like our target star. Our target star is the white star with the crosshairs in the middle here. That would make it that, I would think. So I bet that's my target star. And I would be pretty confident about that. Yeah. Okay. So hover your mouse, and if you want to zoom in, you can use this wheel zoom option over here, and you can zoom in on your target star. So put your mouse over the target star, and it says, okay, the X and Y coordinates, and you may want to write this down on a piece of scratch paper when you're doing it for yourself, but all right. So my target star is at y equals 1513 and x equals 1513 and y equals 1024. I would not leave it as the E notation. I would just convert it into a decimal. So 1513 and 1024 are the coordinates for my target star. So if I come down here, it says enter the coordinates for your target star in the format, and now it needs to be formatted like open brackets, and then the x coordinate was 1513, and the y was 1024, close brackets. I'm going to hover my mouse over here just to be sure I did it right. 1513, 10, well, it's 1026 now. It's okay if you're off by a couple of pixels. The program will still be able to figure it out. But okay, so that's the coordinates for my target star. Press enter, and it's going to say, okay, now enter, let me shrink this down so you can read the whole thing, enter the coordinates for your comparison stars in this same format. So I got to find what my good comparison stars are going to be. Let me zoom in a little bit more again to make this easier for us all to see it. Okay, so that one makes a good comparison star. The good comparison stars are the ones that are numbered over here. So if this star is, I'll zoom back out so I can see my whole image, and if I want to pan, I'm gonna, there we go, pan around here. All right, so then that would make a good comparison star. That one right there is number 96. So that star is at 16, is that x equals 1664 and y equals 421. So I'm going to write that down here. There it goes. Okay, so 1664 and 421. Okay, and then it needs to be in this format. So you're going to start your list with an open bracket, and then each of the coordinates for your stars should also be in open brackets in x comma y coordinates, and then separate them with commas. So I'm going to say open bracket 1664 comma 421, close bracket comma open bracket for the next star. So let's find another comparison star. If this whole thing is rotated, then that star there is going to be this one up there. That looks plausible. Okay, so this one there is 2027 and 1092. So 2027, 1092. Okay, let's find one more. Here's the thing. The more comparison stars you have, the better the quality of your light curve is going to be. So for our purposes, for my purposes of a demonstration right here, I'll just find one more. But for your project, I would say at least 4, maybe 5 would comparison stars would be best. If there are 5 in the star chart here. Is that bright one there? That one? It's gotta be, right? Yeah, it's gotta be. Sure, let's try that one. So that one's at 2239, comma 1914. Oops. What did I just say? 2239, 1913. Okay. 2239, comma 1913, something like that. Okay, so that'll be my third star, and then end the list with the close brackets. All right, and then hit enter. Okay, and now I'm going to zoom out so we can read all of this. Okay, initialization file created. Fantastic. If you want to change anything about the inits file, I don't think you should need to. I think it's probably pretty good to go. So it should be done. Now, if everything goes right, we've told the program where our target star is. We've told it where the good comparison stars for it to compare the flux to are. Now we should be able to just run. And then it's going to check some things out. If everything checks out good, then it'll say, okay, would you like comparison stars added automatically from AAVSO? You can say yes or you can say no. I mean, you've already added comparison stars from AAVSO. Honestly, whether you say yes or whether you say no, you're going to get pretty much the same results. So, in order to save time, I would just say no. But you know what? If you want to try and say yes, well, let's just say yes. Let's see what happens. I honestly think things aren't going to change very much. All right. Um, a lot of times, what happens is you'll say, "Yeah, sure, add your own comparison stars, go nuts," and and then a message will come up in a minute saying, "Yeah, we didn't find any." So you're like, so nothing really changes from having them add their own. Um, so if you say no, it'll just skip that step. But whatever, it's fine. Um, all right. So as long as now is the slow part because it's gonna run and analyze all 453 of my images. So this step is gonna take a while. But as long as that pinwheel is still running up there, then you know everything's okay. It's retrying to verify. Software caused connection abort. That doesn't sound good. Hmm. Okay. Um, well, again, as long as the pinwheel there is still spinning, that means it's still thinking, it's still working on things. So usually, if something goes wrong with one image, it'll just skip that and go on to the next image. And so if it doesn't like that one image and it skips it, that's fine. You've got hundreds of images. If a couple of images just get skipped over for being not helpful or not compatible or not useful, then you've got hundreds of images to keep going on. So it should be fine. So, um, all right. Um, I'm gonna look over at. I'm gonna go back to the Google Drive tab, and what you'll notice is hmm hmm. Oh, nope. Okay. Uh, okay. It's not liking analyzing image 129, which is all the way down there. Huh. Okay. Well, that's probably a good sign then, because if uh, the image number is this number right, oops, right here, 97, 98, 99, 100. So if it started at image 97 and it got all the way to image 129 before it had a problem, then that's probably a good sign because it went, it skipped over this one and it's probably well through analyzing, and so it that one image gave it problems, but it's still processing through the rest of them. Um, what I was going to say a second ago is um, at this point in your procedure, Exotic will have created a second folder that has the same name as your original folder, but then after that it says output. Um, and oh, here we go. So initially, the only file that'll be in the output folder will be this inits.json file, which is the initialization file that it created in order to start running the program. Once this is all done, So it's still running, everything's fine. Once Exotic is done running and analyzing all of your images, then it'll fill up this output folder with a text file and a couple of final light curves. And so those, to show you, this is when I ran this a year ago, the light curve will look like this, where this is the final output, right? It's taken, each of these gray data points is one of the images, and it measured the flux relative to those comparison stars, so before the transit, during the transit, and then at the end of the transit. And it fits that light curve to the red line. The red line is sort of the idealized, this is what the transit should look like, and it gives you two big outputs. The radius of the planet here, and then the time when the middle of the transit happened. Those are two of the big conclusions these are two of the big results that you get from this analysis, from this observation. And so those are two of the big results that you're going to report in your paper, right? So, but it can't produce these curves until it's done analyzing all of the images. And let's see. Okay, it's downloading some information. It's downloading some more information. It is okay. It's running. It's doing its thing. I think that's probably a good sign. This is going to take a little while, right? The full procedure of running the code is going to take a little while, and you don't need me to watch to record this whole video, but in the end, once it's done analyzing all of the images, it'll probably print out line by line, analyzing image, well, in my case, analyzing image 97, analyzing image 98, and analyzing image 99, etc., etc. Is that what it's about to do? So that'll take a while. There's nothing for you to do. You can just walk away, leave your computer running, and actually this isn't being done on your local computer. This is being done in the Google Cloud servers. So you can step away, and an hour later, if all goes well, you will have at the bottom of your screen a printout of the light curve with all of those results printed right there. You don't need to save them because they'll already be saved into that output folder, and then those are your results, and you're ready to start analyzing those results and then preparing for how you're going to explain the results in your paper. All right. Okay, so what it's doing here is it's taking the comparison stars that I entered, which for me, I just put in those 3, but you're going to put in 4 or 5, hopefully. Okay, and now there we go. It's starting to analyze each image. There it says no comparison stars were gathered from AAVSO. When up here when it asked, do you want it to find comparison stars from AAVSO, you can just say no. I don't think it'll make any difference. It'll probably save a second of computing time. And here it goes. And now it's just analyzing each individual image. And now you're just going to let it run for a while. Come back at the end. At the end, it should print your light curves there on the screen, and give you your results. I'm just going to pause recording here, and I'm going to let this run, and then I'm going to skip to, I think I'll start recording again once it has some results produced so that you know what they're going to look like. So, all right, I'm going to pause the record here and then cut to when this is all said and done. Okay, flash forward to half an hour or something later. It says, end of production process, Exotic has successfully run. It is now safe to close this window. And then you'll see, okay, it produces a version of your image. Um, Here's the light curve, which looks a little bit different than the one um, that we looked at a few minutes ago. So that's interesting. Hmm. Might have to dig deeper into that. Um, but still, the trend line, the red curve, matches the data points pretty well. Um, and and then you've got these complicated graphs here that are essentially showing you sort of the ranges of possible values, and um, because the radius of the planet will affect when the middle of the transit is, there's sort of a relationship between the two, and so you create this region um, where here's the best fit, like here's the region of the best fit, and then it compares all of these to say, oh, okay, well, the radius of the planet is, the best fit here, the best value is the 0.17. Here's the best fit for the mid transit time. Here's the best fit for the semi major axis, the ratio of the semi major axis to the radius of the star. This is not exported to your output folder, so you could save this image if you want to, and if you wanted to report it in your paper, I think you might be making more work for yourself if you want to explain what this is. But it might be useful for some things. You might want to save that for something or other. But really, like, this is the big output, right? Your light curve, where it helps you figure out the radius of the planet and the mid-transit time. Those are the two big results. So, yeah, save these three images. They might be useful or important for analyzing your results in your paper. And then everything else should be done. Like, that should be the thing. So, once you have that, then we can look at your light curve and your results, and you're ready to start putting together your paper for how to present and discuss your results. So that should be step 3. All right, go ahead and get started.